Alright, let's solve smallest divisible digit product 2, which is, unironically, the fourth hardest problem on Leetcode right now. So we've got a string and an integer, and we want to get a number greater than num, such that the product of its digits is divisible by t. The reason why we want a 0-free number is because if there's a 0, the product of digits is 0, and 0 is divisible by everything, so it would be too easy. So that's why the problem asks for 0-free numbers. And if no such number exists, return -1. So first, maybe let's look at the example 3. They're asking us to find a number bigger than 11,111 such that it's divisible by 26. The idea here is it's impossible because 26 is 2 times 13, and there's no way to put 13 in one digit, right? And you can't make 13 by multiplying 2 other digits, right? So that should be the first thing we do, is to find if t is divisible by any integer, prime integer that's bigger than 10. Right? If it's not the case, if it's the case, then we should return -1. That's the first easy thing we can do. And the way we'll do it will be to find what I'm going to be calling the kind of prime factorization of t. And after I write the code, it'll be clear why I do this. So the first thing is I just copy t because I'm going to modify t and I want to use t later in the code, so I want to put a copy. And I'll have a t kind of primes dictionary. And the idea is I'll count how many times t can be divided by any integer between 2 and 9, but 9 included, 8 included, etc. This will make sense. But for this, the code is pretty straightforward and resembles what you would do for prime factorization. So we start with 9. Stop at 2, and while t copy is divisible by I, that's an n, sorry. We add 1, that's a default dict. We add 1 to the end, to key I in t kind of primes, and we divide this by I. Alright, this is very standard code. And at the end, if t copy is not 1, it means t is divisible by a prime number greater than 9, right? Greater than 11, I guess. And in that case, we know it's impossible, so we should straight away return. Right? The reason why I want here to store maybe 8 instead of 2 to the power of 3 is because if, maybe let's make an example. If t is if t is 8 and num is 1, 222 is a good answer, like it's correct, but if I want a minimum number bigger than 1 such that it's divisible by 8, it would be 8, right? 24 would be valid 2, 42 would be valid 2. The best is 8 because it's the smallest of all of them. So as long as we can use 9s, 8s, 6s, 4s, etc., we try and use them because we get a smaller number at the end. So that's why this will be important in the rest of the code. But for now, you should agree that after this snippet, if t copy is not 1, we should return -1. Now, first, the complexity is this is log t, because we divide by I every iteration, and so it will be, in the worst case, probably log in base 2 of t. The next thing we will do is find the optimal string if we didn't care about none, right? And this is this will explain why I did this sort of weird kind of prime factorization. And the optimal string is pretty easy to compute. It's as many 2's as I have in my dictionary, as many 3's I have, etc., etc. This is a 4, 6, 7, 8. Right. Should make sense, right? Because I want the smallest one, right? So I want to put the 9's, the big ones, at the end. I want to put as many 9's as I can, which is why here I started with 9, because if I had started with 3, I would have added 3's and never have added 9's, and I would have had a number with more digits, right? So a bigger number, so it's not optimal. And so yeah, that would be the optimal string if we didn't care about num. Now, the problem is most of the time this string will be smaller in size than num. For example, in the second example, 256 is 4 times 8 times 8. So optimal string is 488. But the answer cannot be 488 because 488 is smaller than 1, 2, 3, 4. Right. Hopefully that makes sense. But in some cases, the optimal string is enough. Maybe here, the optimal string, yeah, exactly here, the optimal string would be enough. So we could get rid of those cases straight away. What we can think about is maybe if the optimal string is too small, right, in length compared to num, we could think I just have to add ones, right? Optimal string is 488, but the answer cannot be 488 because 488 is smaller than 1, 2, 3, 4. So maybe I could just add a 1 at the beginning because I want the smallest as possible, and then 1488 is bigger than 1, 2, 3, 4, so I'm happy, right? Fortunately, that doesn't always work. Maybe I'll show an example. Let's try with 4, 3, 2, 1. Right. The optimal string is 488, then I add a 1, then it's 1488. But still, this is smaller than 4000. And so maybe the second reflex would be to add another 1, right? So I could maybe say, well, 11,488 is fine. Unfortunately, there's better than that, right? The best answer is actually 4. 4 Does that work? I think the best answer is this, right? This is 8. No. This is 16, 64, 256. Right, so that would be the best answer. No, there's actually even better. This is even better. Right, if I'm not mistaken, this is the optimal answer, right? And so you can see there's a lot more work to do than just adding ones to the optimal string, and whenever it's bigger than num, we can return it, right? So that's not the case. Just to make sure I'm not spitting nonsense, 4 times 4 times 2 times 8 does get me 256 on my calculator. So yeah, that should be the actual answer. So the idea is we can't just add as many ones as we can, but we can try to add ones as long as the length of optimal string is smaller than the length of num, right? Because if we do as many ones as the length of num minus basically what's missing to get to length num, then we are at the same size of num, and this is the absolute smallest number we can get, right? So if optimal string So if the length of optimal string is bigger than length of num, or optimal string is bigger than num, then we should just return optimal string. The reason is, and I'll explain both, if we have this, length of optimal string is bigger than length of num, it means that we're in a case, it means that we are in a scenario where maybe t is 7 times 7 times 7, sorry, 7 times 7 times 7, and num is 1, right? So the optimal string is already bigger than num anyway. The second if statement is optimal string bigger than num, and that means length of optimal string equals the length of num. And if optimal string is bigger than num, then optimal string is the answer, because optimal string is the smallest by construction number we can get, such that multiplying all its digits gets us t. Right, and hopefully that is clear enough. So the first scenario is optimal string is bigger anyway. Second scenario is optimal string wasn't big enough, we added ones in front of it, and because it's the smallest we can get, then this is the answer, right? And so this should work for this, this should work for this, it won't work for this. I believe it will work for this, because 5 times 5 times 2 is 50. No, never mind, it won't work for that one either. This case is already dealt with because it's -1. So yeah, I believe those 3 cases are dealt with already. We do get a mistake here. So we dealt with the easy sort of edge cases. Obviously there's still a lot of work to do with those kind of hard cases I described earlier. But maybe before that, we should concentrate on the cases where there's a 0 in num already, right? If there's a 0 in num, we can get rid of it, because the statement says the number has to be 0 free. So at least let's our lower bound, right? Let's increase our lower bound such that there's no 0 already in num, right? And so that's, again, pretty easy to do. Num is currently a string. Get rid of the zeros in num. What is get? So yeah, maybe I should have said this is big O of n, right? Because this could be big O of n. And get rid of the zeros in num, which is big O of n as well. The thing is, num is a string is immutable, so let's just have a list of integers to represent num, right? So it's int digit for digit in num. And we'll just iterate. I will call n length of num l in length range of n. If num l I is 0, then I change I to 1, and everything after should also be changed to 1, right? Because, for example, if I've got 509, right, I don't want 519, I want 511, right? Just the first number doesn't have a 0, that's after 509, right? So it's 4j in range I to n, num l j equals 1, and then I break here. And so here I should have sort of a cleaned, clean lower bound, right? The lower bound without the ones, the zeros. So for example, 50 will become 51, right? My actual lower bound here is 51. Unfortunately here, the answer won't be good because my optimal string will say 15. 15 is smaller than 50, and the answer is not 115, right? So I can't just add randomly ones, right? It's the same as this one, we have to do a little bit more work. But before that, maybe the first Again, edge case, it's good to just get rid of all those edge cases. As long as it's big O of n, big O of log n, big O of 1, you can just list even if it's too many edge cases. Let's deal with this one, right? Because this one is already divisible by 50, right? 5 times 2 times 5 is 50 already, right? I believe this is not essential for the way we'll solve it, but I think it's best to just write as much as we can whenever we find a good edge case. So we'll get the product of integers in num mod t, and if it's 0, we'll just return that number, right? We don't have to change it. Right? So the product is 1 for I in range num l, product times equal num li, product mod equal t. Sorry, this is in range n. If product equals 0, we just return this. Right, we can't just return num because the string num hasn't been changed in the getting rid of zeros, but num has, so we have to reconstruct the string. And so that means we have one extra test cases that should be dealt with, so this one should pass now. Right, the first one that gives us wrong answer now is 4428, which is this one. Now we get into the sort of hard part. I think the most important thing to realize first is brute forcing won't work if done incorrectly. And the reason why is, let's take nums equal 1 and t equals 7 times 7 to the power of 10, right? Because t can be really big. T can be up to 10 to the power of 40, and I believe this is way smaller. Yeah, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah, 10 to the power of 9. So this is quite small for t compared to the constraints of the problem. And the answer is obviously 10 7, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. If you just brute force everything from 1 to this, well, it will take you too long, right? This is 10 to the power of 9 operations, and this is way too much to do in 1 second. Or 10 seconds, I don't know what the limit is, but they'll most likely take too long, right? There's the argument that in this case nums equals 1, the optimal string is this, so we would immediately return here, but this is just because my example is not great. If I give you, let me find an example that makes sense. Let's do something like this, and this would be 2 times 7 to the power of 9, and the answer is something like this. The answer is obviously this, and the optimal string is 2, 7, 7, 7, 7, 7, so the optimal string thing won't work. Our edge case treatment. So we can add this to our cases. This is not nums, this is num. And I should be expecting this number. I just thought about it. This is not even the optimal answer. Optimal string is 2, 7, 7, 7, 7, but then the answer is actually this, right? Because in the 6 there's a 2 times 3. And so this is smaller than what I had previously written. So basically, brute forcing won't work if it's done incorrectly, because this would be too long, and our edge cases don't cover everything. This is what I wanted to kind of point out. So to brute force in an efficient way, maybe the first thing to realize is we only care about, if num is really long, we only care about the suffix of num. right? If we look at the constraints, num can have up to 2 to the power of 10 to the power of 5 digits, but because t goes only up to 10 to the power of 14, there is never going to be thousands of digits such that the product is t, right? We only need a small suffix part to do 10 to the power of 14, right? Even if I use 2s, right, which is not even good because I could use 8s, but 2 to the power of like 32 is 10 to the power of 9, right? It's 4 times 10 to the power of 9. So maybe if I go up to 50, right, this is already bigger than 10 to the power of 14. So I don't really need that many digits, and so there will be probably a large part of num that I can ignore. And so the claim is I can ignore the first n minus the sum of these digits of num. Maybe with the plus one. So let's take first an easy example, right? If num equals like random numbers, and then maybe I'll make only ones to make it easy, and then c is 7 times 7 times 7, right? This would be 3. This would be 24. 24 minus 3 is 21. So that means I can ignore those, and indeed I could just put 777 to have the correct answer, right? Here the answer is I don't change anything, I just add 37, say. Right, so we can even add this test case. It's a good habit to make sure our code is correct, and we only have to change. Yeah. There is some cases where we need one extra digit, and the reason is I could have this. Obviously here does not, right? Obviously here it works, and here it doesn't work. So there's very rare cases where, but I need to consider them, where I need an extra digit, right? What is this? I need an extra digit that I can set to 2. Right, so this digit I'm setting it to 2, and now I can use 7s here because this is bigger than this, because this digit is bigger than this digit. Right, so this is why I will maybe need n minus the sum minus 1 digit of them, right? And this is important that I did not use the prime factorization, but this thing I called kind of prime factorization, because if I had t equals 8, right, I only need 1 or 2 digits. I don't need like 3 or 4. Instead of saying 2 to the power of 3, I just say 8, which makes sense because I'd rather only touch 1 digit than touching 3. And so this is the first thing we'll do to find this shortest suffix. So let's find this shortest suffix I can look at. Again, this will be big O of n. The only problem we would have is if I have something like 999, right? I would need 4 digits, right? And basically I need to find the first digit that's not a 9, right? Maybe I'll give you an example here. Here, if I had a 9, right, I would have to start here. Right, so it's not I can ignore the first n minus sum minus 1 digits of num, it's I can ignore up to the first n minus sum minus 1 digits of num. Because here, if I had only 9s, right, I wouldn't be able to ignore anything, right? I would have to add a 1 here. Maybe I should click. I would need to add a 1 here and get those 3 7s. And I'm pretty sure, yeah, that's the best we can do. Oh, my bad. No, if I add 1 here, then everything becomes odd. Sorry. But basically, sometimes I can go to the first positions of num, right? So I'll start here, and then if it's not a 9, I'm happy. If it's a 9, I'll go here, and then I'll go here, and then I'll go here, etc. So it's basically a loop. And I want to be able to say I want to add a digit instead of just saying I want to find the shortest suffix. So the first thing we can do is just say num_l.insert. This is bigger than n, that's okay. Just so that we have a fake 0 here, right? So that we can just say, oh, this is not a 9, I can set it to digit +1. And I'll call this mid, even though it's not a mid, but it's basically when do I start caring about changing the numbers, right? When do I start caring about changing the numbers? The digits. So initially it's -1. I'll start here. Obviously after inserting, I need to just update the length. And then I'll end at 0. And if num_li is different than 9, mid equals I break. If mid equals -1, meaning if I had to go all the way back to the beginning, it means I can just create this optimal string very easily, right? This is just 1 plus optimal string. Because optimal string is the smallest we can get after this one. So I can just return 1 plus optimal string. Obviously, this doesn't work in cases like this, right? In cases like this, I would have mid, which is here, the first one that's not 9, and the optimal string is still like this part, and that still doesn't work. So that's almost sort of basically another one of those edge cases. But now we know we only have to care, from now on, we only have to care about num_l mids up to the end. And I say this, but first, before saying actually this, I should compute what they contribute to, right? Here there was no 7s here, but if there was a 7, it would have been practical, right? Maybe there was 3 7s, in which case I would not have had to change anything, right? So I need to know what's in there, basically. And to do that, I'll just do product up to mid, ones for I in range, mid, product up to mid, times equal num_li, and I'm take the modulus. This is important, otherwise it's probably going to time limit exceeded, because we deal with like huge numbers, right? 2 to the power of 1,000 is way too big for your computer to handle correctly. And I also want to know what are the primes I still need to add. Right? Here, if I do the product up to mid, I would get a number, and then I would want to know I need 3 additional 7s, right? If I wanted to finish my number. Right? And here we'll talk about primes, real primes, because I have to be careful with 6s. We can't say I need more 6s, right? Because we don't know if we want to use 6s or 2 times 3, etc. Right? So here we'll stop using the kind of weird factorization, prime factorization, but we'll use a real factorization. We'll basically copy paste this, except for the real primes. We'll use t copy again because we don't want to lose anything about c, and here we'll just do for I in 2, 3, 5, 7. The only primes smaller than 10. Call this t primes, and that's all. And we'll do remaining primes, right? Which is initially just a copy of t primes. And every time we encounter a number, we can just say, well, we've done this prime already, so we can just it's not a prime we need to care about, right? If there was 7s here, we would get, initially there's 3 7s to add in this suffix, but then if there's 1 7, only 2, if there's 2 7s, only 1, if there's 3 7s, I don't even have to care about 7s anymore. So here, if num L I is in 2, 3, 5, 7, I can just say remaining primes num L I minus equals, I won't say minus equal 1s, I'll say the maximum between 0 and minus equal 1s, right? Because here, the primes of t are 7, 7, 7, and when I encounter 6, I don't want to have weird negative numbers in my remaining primes dictionary. If it's 6, if it was 0 and I encounter 6 or 5, I don't want the 5 to change to minus 1. I want to stay to 0. I don't need any more 5s. And then I have weird, not weird, but like the trickier digits, right? For 4, it would be remaining primes of 2 is max of 0 minus 2. 6, I would remove 1 and 2, 1 and 3. 8, I remove 3 to the remaining primes 2 because 8 is 2 times 2 times 2. And 9 is, I remove 2 for 3s. Compilation, what is this? Yeah, no, that makes no sense. So that would be for number I. And then now, here, I know what primes I need to add to get t. I know which parts of num I can ignore. And so maybe the brute force will be more legitimate. We'll see that it's still not good, but we're getting closer to having a brute force that actually works. Right, we want a complexity that's not, we want less than 10 to the power 7, 10 to the power 8 operations, basically. And the way we'll brute force through the number is basically to do that first search, and we'll, maybe if I get this again, we will try this one, then this, and then this, and this, etc., etc. And we only want to increase those numbers, right? This is illegal. This is illegal because smaller than none. However, if instead of 1 here I put a 2, right, then those I can put whatever I want. Not illegal because 2 is bigger than 1 and the rest of the string doesn't matter. And you can see very easily how we would still have the same problem. Right, if t equals 7 times 7 times 7, like loads of 7s, I believe this is still smaller than 10 to the power 14. Right, this is not actually smaller, my bad. Right, this is smaller than 10 to the power 14, this number. However, if and num is maybe something like this, then I will have to go through everything. I would have to go through everything from this to just some 7s, I think. Right, now which is like here, how many you have? 11s. Like I would have 11 numbers, so 10 to the power 11. I don't know if I have 11 7s here, but it would be too much. I know this is dealt with the edge cases in the beginning, but you get the point. We can still code it, and then we'll see how we can improve it. The important part is to understand, here I can do whatever I want if I did increase a digit on the left. Right, so I'll have a DFS with 2 arguments. That returns the boolean. The boolean return would be if it's a valid. If returns true, I found a number bigger than num that the product, the digits of which multiply to 2. Right, and the first one I find because I'll go through them in increasing order. The first one I find will be the one I return, because it's the first one that's bigger than them. And 3 means, have I increased on the left the number? If I haven't increased, then I'm constrained. But if I have increased, I can do whatever I want with the left digits, which I was explaining just a second. And I will update products up to mid to avoid recomputing the multiplication of all the digits. Right? I'll just update this as I go through my DFS, which is very standard. We do this kind of DFS. So if the index, the first base case, if the index is equal to n, the end of, where is n? Yeah, I have refreshed it, updated it. If the index is at n, well, I just return whether the product up to mid equal to 0. Right? This is what just thing. If I'm not at the end yet, I don't want to conclude yet. And then for digits in range, so from 1 to 10, because I want to modify the digits from 1 to 10, except for, because I inserted the 0, right? I want to be able to leave this as is, right? I don't want to change the 0 to 1 necessarily. So I'll do something like 1 if index is different than 0, else 0. So this is only for numbers that would stay with 0, right? Because maybe 0, 9, 7. T is 9 times 8, then I would have to increase this by 1, right? But I don't want this to increase, right? This digit can stay as it is. But this would be the only one that can stay as it is. So first of all, if I'm not free, meaning there's no one on the left that allowed me to do whatever I wanted, I need to make sure the digit I'm going to replace number index with is bigger or equal, right? So if it's smaller, then value change, right? For example, num is 097 and index equals 2 and digit equals 6, right? I'm not allowed to put a 6 here. So I'll just continue. Then I will update remaining primes. So if digits in 2, 3, 5, 7, I just do remaining primes digit minus equal 1. Just because I add a new digit. It could be the same as the one that was in num, right? Because digit can be equal to num. But because remaining primes only care up to mid, I have to update it. And then I have to do the usual. If digit is 4, minus 2, if it's 6, this, if it's 8, minus 3, if it's 9, minus 2. For 3. Yes, minus 2 for 3. And obviously, because this is a DFS, it will be the same as the longest path algorithm. At the end, I need to just revert my changes. Okay? Because I can change 097 to 098, but I can also change 097 to 099, right? Just to make it clear, 097 will go to 098, then I'll go to 099. And when I go to 099, I don't want to carry over the changes I done when I had the 8, so I have to revert them. And here I say numL index equals digits. Again, I want to revert everything, so I need to be able to remember what the old number was. Old numL index is this. Similar for the product up to mid. Product up to mid will be times equal digit. Actually, it's a bit more complicated. It would be product up to mid times digit modulus t, right? Because I'm computing this modulus t, except if digit is 0. Right? If the digit is 0, it's because I'm changing the first one. It's kind of the weird change. I don't want to multiply by 0 ever, because that would ruin the whole thing, right? The 0 never counts. It only counts when I put it to 1. It's sort of a placeholder. I'm talking about this 0, which is the only one there ever will be. And then I need to do call DFS, and then I'll just put everything back. Product up to mid is back to old, and revert or sort this. And here the only thing I do is if DFS index plus 1, and then we'll see, then return, right? And here, if I was free, because I had increased something on the left, I'm staying free, so it's free. Or I can become free, and I become free if I change digit and it's bigger than old num L index. Meaning that was an 8 at this position, now I put 9, so I become free. If I was an 8 and I stay 8, but I was free before, well, I stay free, right? So this is what this condition says. And if I don't get anything true after changing this digit to everything I can, then I can return false. Right? And then I can just do DFS mid false. Whenever I find something, I return true. So the numL would be where I want it to be. So I can just return. Where's it complete? Yeah, sorry. And then I can return dot join character for character in numL. Right. There's the only problem is there's this 0 I've added. So I'll just return this if numL 0 status is 0. Otherwise, I return everything, right? So maybe I had 097, it became 098. I don't want to return the 0. But here 097 became 112. I don't know. That doesn't make sense. 115, right? Which would be a valid case, and then I would want to return the first one, right? So that's why I'm doing this. And so this should work, and it should just be too slow. So let's see if it works. Never mind, I made a mistake here. When I do product up to mid, I do it after inserting a 0, so I need to start at 1, right? Otherwise this will just be 0, right? And so this just won't work. And another mistake is just this was not true, right? I wanted 1, 2, and 9 sevens. Here I have 1, 2, 3, 4, 5, 6, 7, 8 sevens. So this has to be a 7, right? And the 2 is contained here. So that was just me earlier that basically said something that didn't make sense. Again, I made a mistake. That was valid, but that was better than that. I didn't have to change the 3, and I could join those 4 and 2, and this was 4388 is smaller than 4428, and 4388 is valid. Right, so that was just me who wrote something wrong earlier. So actually my human brain didn't perform as well as my code, and ironically. Right, so now this works, and I think this will be correct, except as I explained earlier, it will take too much time, right? And we'll see later how we can just make this a lot faster, easily, actually. So yeah, as expected, we get a time limit exceed, right? And the way we can deal with this is, and maybe I'll take an example to illustrate this. Let's take this one. There's a lot of work we're doing that doesn't need to be done, right? Here, I'll first check this, right? So first of all, we said we didn't care basically about anything before that. So let's just put in vertical bar, just so we can know what we care about. And the first thing I'll do is I'll add a 2, maybe, right? Or maybe I can, maybe at one point I'm adding a 2 here. Maybe that makes more sense. And I've added a 2 here. And as I'm entering index here equals 3, or maybe this plus 3, what I'll do is I'll check this, I'll check this, all the way up to this, right? The thing is, I still, like my remaining primes dictionary, I still need 3 sevens, right? But because I'm at index length of the string, or length of numL minus 2, I only have 2 sort of degrees of freedom, right? But I need 3 primes. There's no chance I'm doing anything, right? And you can see I'm doing a lot of work for no reason, right? So this is one way we can get rid of a lot of useless work, right? And basically we'll add a new base case, which is if the mean length needed for, and we'll give it remaining primes, right? Because with this dictionary you know how many digits you need. If this is bigger than n minus index, right? If index is 1, sorry, if index is n minus 1, you only have one degree of freedom because you had the last part, right? If n minus index is 2, in my example, is n minus, if index is n minus 2, as in my example, I only have 2 degrees of freedom. If this is 3, which is again the same as my example, then I don't even need to do anything, it will just return false, right? So I just need to code this function, that's not too complicated. I'm going to code it outside. So we'll just do def this, remain primes, the dictionary, and this will return an int. And so we'll say, and so we'll have to be careful, right? Those are not the kind of prime factorization, so it will be a bit harder than this. So we have to do, I take as many 9s as I can. So this will be, we'll call this result equals remaining primes 3 divided by 2. Then I take as many 8s as I can. Then I take as many 7s as I can. 6 is a bit harder. I've taken some 3s and some 2s already. So I'll do the minimum of the 3s remaining and the 2s that are remaining. But remaining didn't change. This is actually wrong. This is this modulus 2. And this is this modulus 3. Whatever is remaining after this operation, and the minimum, because I need, if I have 2 2s remaining and 1 3 remaining, I can only do 1 6. Then I take as many 5s as I can. I take as many 4s as I can, so this is even harder. This is result plus equal whatever is remaining from this, which is this, minus how much I took in there. And then I take as many 3s as I can. Again, this is kind of similar to this. This is, except I'm using that one. And then I take as many 2s as I can. So yeah, this was actually integer division by 2, and this is the same except it's the remainder. And then I just return results. We can just maybe do some tests. I'm expecting mean length needed of empty dictionary being 0. If I have 1, 1, 1, 1, how many primes do I need? In minimum, I need at least 3, not 4, because 2 times 3 is 6, so I can just use 1 6, 1 5, 1 7. It's not how many primes, right? How many digits. Then let's do 0, 1, 1, 1 is 3 as well. Let's do maybe just 3, 0, 0, 0, and here's 1. 1 is 1, 8. Maybe let's do 2 and just that remain. Right. Yeah, let's just run that to make sure we're good. Right. Oh. And so yeah, if I need, in an ideal world, 7 digits, but I only have 5 degrees of freedom, I don't even have to go through them. So I'm saving myself 10 to the power 5 iterations of this, which is great. 10 to the power 5 iterations, yeah, just not of this iterations. Full period. And so this, first of all, let's check if it's still correct. Yeah, it's still correct. And so this should be reducing the time complexity, and we can talk about it later, but let's see how much faster it is by just submitting this first. This is maybe, what is break Leetcode? Should have removed it. Never mind. I know what's gone wrong. When I do -2, if it was a 0, it will go to like -2, right? But I can't do the max as I did here because I need this information. If I did max, 0 would stay 0, and then when I do +2, I'll get +2, even though initially it was a 0. So that's not good. So I just need to be careful here. I need to just take the max of this and 0 every time. Right? This, then m will be just a function that just returns the max and 0. Right. Alright, this is good, this is good, this is good like this. I hope I'm not making any typos. It'd be annoying. Right, and m is just literally def m of x is return x if x is bigger than 0 else 0. And this should be better. Right. So this works. Now maybe let's talk about why it works. And here, maybe I'll wave my hand a little bit, and feel free to tell me if I'm completely wrong, but I don't believe I am. We are going through numbers in increasing order, right? Correct, because of this loop. So the first number we find is the best one, which is why the algorithm is correct. And so you may think, well, basically at each digit, I have 4 possibilities at most. And the reason I only have 4 possibilities at most is because if I need an 8 and I add a 4 or a 2, then I will need more digits. I'll need extra digits, right? But we started at mid, right? And we only gave ourselves one. No, where is mid? Sorry. We started at mid and we only gave ourselves 1 digit for breathing, right? This digit, right? So if I'm doing something suboptimal, right, I'll be punished very fast thanks to this. I'll be punished very fast, and so I won't lose much time, right? So every time I add a digit, or change a digit in num L, I'm basically adding the right one, right? Because if I need an 8 and I'm putting a 2, I'll be punished quick. If I need an 8 and I'm putting a 3, or if I need an 8 at this position in the actual answer, then I can't be allowed to add a 3, because adding 8s should be done at the end, right? So I only get to 8 if I actually need an 8, right? Or in the other way, if I'm at the beginning and I need a 3, I won't even go to 8 because I'll add 3 and then I'll find the answer. So eventually I'll barely do any work, right? Because I always find the right answer. If I add a digit that's too big compared to the optimal, well, that doesn't happen because I'm going through numbers in increasing order. And if I add a digit that's smaller than optimal, I'm in this kind of situation, then I'll be punished very fast. Right? So at the end, I only do d, which is 10, the number of digits, times n, which is 10 to the power 5, things. I don't do much more. I do some sort of constant time thing, so maybe I can even add a times 10, but that's, you know, barely anything. And this is the actual worst case, because most of the time the numbers before are kind of helping, right? Here I put 7 times 7 times 7, but if I had something like 2 times 7 times 5, right? Well, I already have a 5, I already have a 2, right? So usually the beginning of the string helps me. So this is really, really the worst case, and I would struggle making a test case that it's actually the worst case, and this is kind of hand waving. But because we're going through numbers in increasing order, we find the optimal answer first, and whenever we make a bad choice, we're immediately punished by this sort of base casing. So that's why it's very fast. Yeah, that's it.